Far beyond the constellations we know, in a distant galaxy whose light has crossed billions of years to reach us, a colossal star, 100 times the mass of our Sun, reaches the end of its short, furious life. For a blink in cosmic time, it will pour out more energy than 1,000,000,000,000 suns combined, a burst so fierce it will send tremors through the fabric of space-time itself. Tonight, we set out to drift along those tremors. We'll wander among explosions that dim whole galaxies, linger at the rims of black holes that swallow even light, and sit quietly with the fundamental forces that hold everything, us included, together. Settle in. Slow your breath. We're going to travel into a power so vast it bends reality, and we'll do it gently. We begin, deep within each atom in your body, atoms that once belonged to stars. An invisible standoff never truly ends. In the nucleus, positively charged protons huddle together, like a crowd of giants pressed shoulder to shoulder, each one repelling the others with a force that should fling them apart in an instant. If only electromagnetism had its way, there would be no atoms, no chemistry, no you. Yet there they are, bound fast, held in place by the strongest interaction in the universe, the strong nuclear force. This force is peculiar and supreme. It acts only across unimaginably short distances, smaller than the width of a single proton. But within that tiny range, its grip is absolute. Measured against other forces, it's staggering, roughly 100 times stronger than electromagnetism, and so many orders of magnitude beyond gravity that comparisons begin to sound like myth. If gravity were the faintest whisper in a quiet hall, the strong force would be the sudden crack of thunder shattering the air. The strong force works through messenger particles called gluons. Imagine invisible cords woven from pure interaction, lashing quarks together to form protons and neutrons. These cords do something startling. The more you try to stretch them, the stronger they pull back. Like a rubber band that grows thicker and more stubborn the farther you tug, the strong force resists separation with increasing fury. Physicists call this behavior confinement. You can hurl energy at a quark to rip it free, but the energy you add simply congeals into new quark-antiquark pairs and more gluons, spawning fresh links of the chain instead of breaking the old ones. It's as if you tried to cut a chain only to watch new links grow in the gap the moment your blade passed through. Inside each proton, 3 quarks whirl and jostle in a coruscating storm, somewhat like dancers in a hall of mirrors where even the mirrors are made of motion. The gluons that bind them aren't passive threads. They carry the strong force themselves and interact with one another, knitting a web so intricate that even our most advanced supercomputers struggle to simulate it precisely. At these scales, distances are counted in femtometers, 1/4,000,000th of a meter, so small that the very notions of space and time take on a restless, shimmering quality under the rules of quantum mechanics. This force writes the blueprint for matter. It decides which atomic nuclei can exist and which are forbidden by nature's accounting. It sets the pace of stellar fires by determining how the fuel in star cores fuses and for how long it can burn. It mediates the balance between creation and collapse in every star's heart. Strip the strong force away and watch the world vanish. Protons would fly apart under electromagnetic repulsion. Nuclei would never take shape. Stellar fusion would never ignite. The universe would be a thin, lonely sea of hydrogen atoms and stray electrons drifting in the dark. And yet, for all its strength, the strong force lives in a tiny kingdom. Its influence fades at the edge of the atomic nucleus, about 1/10,000,000,000th the width of a human hair. Beyond this miniature realm, other powers govern. So let's take one quiet step outward, into wider space. where distances tower and time stretches, and watch what happens when gravity, light, and the debris of dying stars conspire to make the most violent spectacles we know. Somewhere out there, a lance of energy, pure and hard-edged, slices through the dark. For about 10 seconds, no more than a few calm breaths, it emits more power than our sun will make in its entire 10 billion year lifetime. This is a gamma ray burst, the fiercest kind of explosion we've found in the universe. These astonishing events are born when the greatest stars meet their end. Picture titans with 20 to 100 times the mass of the sun, roaring through their fuel at a pace that would exhaust our sun utterly in mere millions of years. When the fusion fires that prop them up finally gutter out, gravity claims its due. The core collapses, and from the poles of the collapsing star, twin jets of matter and radiation erupt at 99% the speed of light, velocity so high that even time seems to lean back and watch them pass. In the newborn chaos at the center, a black hole forms, wrapped by a disk of matter heated to incandescent fury. Magnetic fields, squeezed and twisted by the collapse, behave like cosmic railguns, channeling energy with uncanny precision. The jets tunnel through the dying star as if it were tissue, burst free, and remain astonishingly tight and focused across distances that beg a human sense. Imagine a laser pointer holding a perfect spot from Earth to the nearest star. Now magnify that feat 1,000,000-fold, and you are only beginning to glimpse the discipline those jets maintain. A single gamma ray burst can outshine 1,000,000,000,000 suns. Were our eyes sensitive to gamma rays, such an event would blaze brighter than the full moon, even from galaxies billions of light years away. In the briefest instant, the released energy dwarfs what 10 trillion hydrogen bombs could produce if they detonated every second for the entire age of the universe. There was one so bright that astronomers nicknamed it the Boat, the brightest of all time, in October 2022. Its fury overwhelmed detectors throughout the solar system. From roughly 2 billion light-years away, it even nudged Earth's upper atmosphere, an almost unthinkable reach for a flashing heartbeat of a dying star. If you're enjoying this gentle voyage through deep time and deeper forces, and you'd like more stories told in this calm, sleep-friendly way, you're warmly invited, without breaking your drowsy mood, to subscribe to and like Space Historian. It helps this quiet corner of the cosmos stay lit for you. The light from such bursts arrives after journeys longer than any storybook odyssey, bearing news of deaths that happened before our planet had formed, before our sun had ignited. Some come from epochs when the first stars were only just kindling, less than 1 billion years after the Big Bang, when the universe's giant stars lived fast and burned with a savagery we scarcely see today. These ancient lighthouses let us peer into the early universe, into generations of stars that lived and died to spread the heavier elements, carbon, oxygen, iron, that later worlds and living creatures would need. And yet, vast as these titans are, they still dim beside the oldest powers lurking in the dark between galaxies. At the center of the Milky Way lies Sagittarius, our Plox, a black hole about 4 million times the mass of the Sun. It is tame by the standards of the true colossi. Some supermassive black holes pack 40 billion suns worth of mass into a space smaller than our solar system. They are like drains in the structure of reality, where space-time curves in upon itself so steeply that nothing, no particle, no beam of light, may claw back once it crosses the point of no return, the event horizon. Around them, space flows like water in a whirlpool. Time itself bends in ways that, if we didn't witness their effects, would seem like fables. These monsters did not simply sit and grow for eons like patient trees. Observations reveal that the most remote quasars, dazzling beacons powered by ravenous central black holes, shine at times when the universe was still very young, less than 1 billion years old. Somehow, within that brief dawn, some black holes swelled to billions of solar masses. Ordinary stellar death cannot account for such headlong growth. One leading idea suggests that, in the early universe, immense clouds of pristine gas collapsed directly into massive black holes, skipping the star stage entirely. These direct collapse seeds may have started life already harboring hundreds of thousands of solar masses. With that head start, they could feast on surrounding gas, swallow stars, and merge with other black holes to balloon into giants. When gas spirals down a black hole's gravity well, it doesn't fall silently. Friction and compression heat it to millions of degrees, and the infalling matter flattens into an accretion disk that shines so fiercely it can outglow 100 billion suns. In the inner reaches of the disk, matter orbits at a good fraction of light speed. Time for those particles slows relative to the outside universe. Seconds stretch, minutes lengthen, and relativity becomes not an abstraction, but an intimate condition of their motion. The brightest quasars are visible across the observable universe, cosmic lighthouses whose beams are powered by the mealtime fury of black holes. They can blaze brighter than all the starlight in their host galaxies combined, a single hungry engine drowning out hundreds of billions of stars. Sometimes these feeding black holes fashion colossal jets, narrow streams of particles hurling away at nearly light speed, cutting through intergalactic space for hundreds of thousands of light years. Those jets are not just fireworks, they're engines that sculpt the evolution of galaxies. They heat gas that would otherwise cool and make new stars, turning off stellar birth across entire regions for millions of years. In recent years, astronomers have found examples where the central black holes seem oversized for their galaxies, breaking the tidy correlations we thought tied black hole mass to the properties of the stars around them. Such outliers hint that the relationship between a galaxy and its central black hole is more like a long, unpredictable conversation than a simple equation. But all of these wonders, all this drama of light and gravity, plays out on a stage in motion. Across the full spread of the cosmos, roughly 13.8 billion light-years in any direction we look, an invisible influence is steadily winning a quiet war. It tugs not on objects directly, but on space itself, pulling the universe ever wider, faster. We call it dark energy. It accounts for around 70% of everything there is, and yet we barely know what to call it beyond a name that admits our ignorance. Dark energy is unlike the forces we're used to. Gravity and electromagnetism fade with distance. Dark energy doesn't. As space expands, there is more space for dark energy to inhabit, and so its overall push grows. It is the universe's accelerator pedal, pressed gently but relentlessly. Astronomers stumbled upon it in the 1990s while measuring distant supernovae, expecting to see expansion slowing under the collective gravity of all matter. Instead, the data whispered a surprise. The universe's expansion is speeding up. Like noticing that the tide is not only rising, but rising faster with each wave, they realized an unseen agent was at work. You can picture it as a balloon being filled, every point on its surface sliding away from every other point as it grows. Galaxies are like tiny coins taped to the balloon. They don't race across the surface under their own power, rather space between them stretches. The farther apart they are, the faster they appear to separate. This steady widening, driven by dark energy, doesn't stop at the edges of clusters or superclusters. It is a property of the entire cosmos. Something about dark energy also unsettles our intuitions about conservation. As space swells, the total amount of dark energy seems to increase. even though its density remains roughly constant. Where does that extra energy come from? We don't know. One suggestion is that dark energy is a feature of space-time itself, a cosmological constant, an idea Einstein once entertained and later regretted. Others propose a field that evolves in time, a dynamic energy woven into the universe. There is even the possibility that our understanding of gravity, so precise on solar system scales, needs rewriting on the largest scales. Whatever its nature, dark energy holds profound consequences for the far future. If it remains the same or grows stronger, it will continue to drive everything farther apart. The largest structures will become lonely islands as clusters drift out of one another's reach. Stars within galaxies will carry on for a long while, but eventually, if certain versions of dark energy dominate, even gravitational bonds within galaxies could lose their grip. The most extreme hypothesis is the Big Rip, in which the very fabric of matter is pulled apart. First galaxy clusters, then galaxies, then star systems, then planets, but it wouldn't stop there. If the expansion's acceleration becomes violent enough, even atoms could be torn asunder, and the constituents of particles themselves prized apart. It's a chilling picture painted on an impossibly distant canvas of time, where the gentle push we barely feel today becomes the last great undoing of structure. Let your breath soften. We are going to turn from the grandest of scales back to the most compact wonders known: neutron stars. Imagine compressing a mountain into a sugar cube. Then consider that this still wouldn't be dense enough. Neutron stars contain the sun's mass pressed into a city-sized sphere about 12 meters across, the density so extreme that space-time itself buckles fiercely around them. Starlight skirting their surfaces bends in curves that would seem like magic were they not measured and mapped, and yet, astonishingly, gravity is not the most unsettling thing about them. Neutron stars cradle magnetic fields of an almost inconceivable strength, trillions of times more powerful than Earth's protective field. These fields snare charged particles and sling them to near-light speeds, forcing them into tight, roaring paths. As the star spins, these beams sweep through the dark like the slow wink of a cosmic lighthouse, pulsing across the void with a rhythm as steady as a heartbeat or as frantic as a drummer's roll. Some rotate several hundred times each second, their timing so precise that, from across thousands of light years, they serve as celestial clocks. The beams we detect, radio waves, X-rays, even gamma rays, are not mere glow. They are the driven emission of particles whipped by ferocious magnetism, powered by the fundamental forces of the universe. The magnetic hush around a typical neutron star is so intense that, even from 600 meters away, it could wipe every credit card on Earth clean as a slate. Drift closer, say 1,000 kilometers, and the field would be strong enough to tug at the iron in your blood, coaxing it ever so slightly toward the star. In such company, even emptiness takes on texture. The field lines, normally invisible, reveal themselves in ghostly threads as they snare and funnel charged particles into tight luminous streams. When the star spins, and many do, their beams sweep the dark like metronomes for the cosmos. We call those spinners pulsars, radio and X-ray lighthouses whose pulses arrive with the unfussy regularity of master clockworks. Some whirl more than 600 times each second, faster than a kitchen blender, yet keep time with a precision that rivals our finest instruments. Each tick is a full rotation of a stellar remnant only a few city blocks wide, turning flawlessly in the deep. The surface of a neutron star is a landscape where ordinary matter forgets how to be ordinary. The magnetic field is so overwhelmingly strong that atoms are stretched into needle-thin strands, aligned obediently with the field lines. The neat shells and orbitals of atomic physics dissolve, replaced by exotic states that exist nowhere else. And any material that falls in, dust, gas, a wayward pebble of rock, doesn't arrive with a thud. It is squeezed into a paper-thin layer in an instant, its structure crushed by gravity into a skin only millimeters thick. Try to imagine dropping a marshmallow from waist height. On a neutron star, it would strike with the violence of a hydrogen bomb, unleashing more energy than all the explosives used in the Second World War. Gentle things become catastrophic in the gravity of these objects. A few neutron stars take all of this to a rarer, wilder extreme. We call them magnetars. Their magnetic fields are not merely strong, they are 1,000 times stronger than those of typical neutron stars, brushing against the theoretical limits permitted by physics. When stress builds in their rigid crusts, the surface can crack, starquakes rippling through the shell. In a tenth of a second, a magnetar can release more energy than our sun will radiate in 100,000 years. These flares blaze so fiercely that, from across tens of thousands of light years, they can rattle the upper atmosphere of Earth, briefly changing the way our planet's air conducts electricity. Their reach is a reminder. Distance offers safety, but not always insulation from the universe's sharpest events. In magnetar country, even the vacuum is different. Space itself behaves like a strange, birefringent crystal under the magnetic pressure, splitting light into polarized paths as it passes through. Photons, usually indifferent to one another, begin to act as if the space between them has texture and grain. Observing that polarized light gives astronomers a direct clue to field strengths we cannot hope to reproduce in any laboratory. It is a kind of gentle fingerprinting, evidence left not on dust or gas, but on the nature of light's passage itself. While we stand in awe of these compact remnants, they are only the threshold to the universe's most speculative marvels. Stretching, perhaps, from one side of the observable cosmos to the other, are hypothetical filaments so thin they make a hair look like a tree trunk. Cosmic strings. Picture them as one-dimensional threads, narrower than a proton, yet potentially longer than clusters of galaxies. If they exist, they are scars from the universe's first breath, relics of phase changes that rippled through space-time a fraction of a second after the Big Bang, when nature's forces were cooling and separating, symmetry breaking like ice forming in a pond. The cracks you see in frozen water are a fair metaphor. Boundaries where regions settled into slightly different arrangements. A cosmic string would be one of those boundaries written into the geometry of reality itself. Their density defies comfort. A segment of string the length of a meter could weigh as much as the Earth. A strand spanning the Earth-Moon distance would stockpile enough mass energy to power human civilization for countless trillions of years, if energy could be harvested from it at all. And yet, despite harboring such mass, a string would be all length, essentially no width, the ultimate concentration of energy into a line. They are where matter, energy, and the mathematics that describe them braid into something at the edge of existence. Should such strings move through space, they would raise a wake not in air or water, but in space-time itself, sending out gravitational waves. Wrinkles no less real for being subtle. The pattern of those waves would differ from those we've already detected from black hole and neutron star mergers, offering a new signature, a new drumbeat. When two strings cross, they can reconnect, slicing off loops that quiver and hum like plucked guitar strings. But the songs they sing are not sound. They are shifting curvatures of space-time, ripples racing outward at light speed. Over time, these loops would radiate their energy away, shrinking and shrinking until they wink out in a last soft shudder of distortion. Even a loop as large as our solar system would, in the grand arithmetic of the cosmos, dissipate in a few million years. Long for us, but a brief rehearsal for the universe. In dreams and equations, some imagine strings as roads we might someday travel. If two distant points were bridged by a string's geometry, the path along it could be shorter than any route through ordinary space. In that conjecture, a craft might arrive before a photon that must meander through the wider universe. It would be a shortcut not by speed, but by cleverness of route. Others think of strings as glimpses into dimensions we do not inhabit directly, solid, fundamental objects in a higher dimensional realm, with only their slender cross-sections showing in our three-dimensional world. For now, they remain exquisitely poised in theory, neither found nor disproved, waiting for instruments sensitive enough to listen for their particular kind of tremor. If you're finding this slow drift through the cosmos calming, and you'd like more night-soft stories about deep time and deeper forces, consider, quietly, without breaking the mood, subscribing to and liking Space Historian. It keeps this lantern lit for your next journey. Now let us return to what we can see blazing across the dark. 4 billion light-years away, a black hole the size of our solar system is launching a lance of particles that pierces an entire galaxy. This jet, a river of plasma so hot it seems to boil in place, surges outward at 99.9% the speed of light. It carries energy enough to power 1 trillion suns, and yet holds its aim, a narrow, unwavering column across distances that swallow the mind. Such jets are born in the brawling, bright maelstrom around supermassive black holes, where matter plunges inward in a spinning disk, and space-time is a tightrope between gravity and magnetism. As the disk whirls, it winds up magnetic fields like cables on a winch, storing colossal energy in their twists. Those field lines become tracks for charged particles, guiding some of the infalling matter out along the black hole's poles. It is a strange alchemy. The same gravitational well that swallows almost everything contrives to fling a fraction of material back into the universe at nearly light speed. The magnetic fields act as cyclotrons writ on the sky, accelerating particles to energies that dwarf what we produce on Earth. From our vantage point, the jets are so unwavering they might have been drawn with a straight edge across the heavens. Even when seen with the fine vision of radio telescopes, they remain pencil-thin lines stretching for hundreds of thousands of light-years, threading the intergalactic medium. Inside, protons and electrons race so fast that their relativistic mass swells by thousands of times, and ordinary matter becomes something more like bullets of pure energy. When one of these jets happens to be aimed almost directly at Earth, we witness a blazer. Its brightness can surge or fade by factors of hundreds in mere hours or days. Knots of turbulence within the jet drift towards us so quickly that geometry plays a trick. They appear to move faster than light. They don't, of course. The illusion is the work of perspective and speed, a magic show staged by relativity when nearly luminal motion comes almost straight at you. It is, if anything, proof that the jet is skimming the speed limit imposed by the universe. The strongest of these quasar jets carry enough raw power to heat the gas in an entire cluster of galaxies, puffing vast cavities in the surrounding medium, bubbles that last for hundreds of millions of years. They sterilize regions that might otherwise condense into stars, turning off stellar birth across volumes so large they take time itself to traverse. Observations have traced some jets far beyond the edges of their host galaxies, out into the wider ocean of intergalactic space, their fossil light telling stories of black hole feasts in an era when the universe was more tempestuous than it is now. Elsewhere, In a quiet corner of a different galaxy, 30 million light-years away, a smaller drama plays out with the poise of a metronome. A white dwarf, the exposed, dense core of a once sun-like star, circles a companion and steals from it, slowly, inexorably. Hydrogen gas trickles from the larger star across the gravitational divide, spreading over the white dwarf's surface like winter snow on a hard stone. The white dwarf is compact beyond intuition, the mass of our Sun pressed into a sphere the size of Earth, matter so tightly packed that a teaspoon would weigh as much as a car. Its exterior glows at tens of thousands of degrees, hot enough to turn any earthly substance into vapor in a heartbeat. Layer by layer, the stolen hydrogen is squeezed into a thin shell. Pressure climbs. Temperature rises. The surface becomes a patient pressure cooker. Fusion begins to smolder in the outermost skins. There is a limit to what holds this star up. The mindfulness of electrons refusing to be squeezed into the same quantum states, a phenomenon called degeneracy pressure. When the white dwarf's mass creeps to about 1.4 times that of the Sun, a threshold known as the Chandrasekhar limit, the balance fails. Gravity's demand overcomes the electron's resistance. What happens next is neither a mere flare nor a collapse, but a runaway. The surface ignition races inward. Carbon and oxygen in the white dwarf's interior undergo explosive fusion, forging iron and nickel in a chain reaction that tears the star apart from within. In seconds, the entire white dwarf becomes an expanding fireball. We call this a Type Ia supernova, one of the most uniform catastrophes in nature. Because they all ignite at roughly the same mass and under similar conditions, their light curves are so consistent that they serve as standard candles, rulers for measuring the darkness between galaxies. For a few weeks, a single dead star burns brighter than an entire galaxy of living ones, then fades as the radioactive ash, newborn nickel and cobalt, decays and releases its energy into the bloom of debris. Such explosions are not just endings, they are forges and couriers. The calcium in our bones, the iron coursing through our veins, the nickel in our coins, elements like these were baked in the hearts of white dwarfs at the moment of their annihilation, then strewn like seeds across space. Shockwaves from Type Ia supernovae barrel through surrounding gas at thousands of miles per second, heating it to millions of degrees. In their wake, they can compress clouds enough to trigger the birth of new stars, even as they lace those clouds with the heavy elements that future planets will need. We carry these events in us. We are, in a very literal sense, made from the yields of cosmic cremation. And still there are dances yet more intimate and violent. Picture two city-sized embers of stars, neutron stars, caught in orbit, their shared gravity binding them in a spiral that has lasted ages. Each is more massive than our Sun, yet only a dozen or so meters across in radius, astonishingly dense, the last stop before the fall into a black hole. Their crusts are lattices of nuclei pressed together into forms we can scarcely model. A single teaspoon of their substance would weigh billions of tons on Earth. As they wheel around one another, tides rise, not in oceans, but in the stars themselves. The gravity they exert distorts each other's shape, stretching and squeezing their surfaces like dough, and the kneading heats them until even these dim bodies glow in X-rays with temperatures of millions of degrees. Each orbit robs them of a little energy, siphoned away invisibly. The orbital dance accelerates as energy bleeds away through gravitational waves. The waves that leak from the orbit of two doomed neutron stars don't ruffle air or water. They pass through everything, dimpling space-time itself. With each lap, those ripples, gravitational waves, steal a little more orbital energy. The theft accelerates as the pair tightens. Energy flows out at an ever-increasing rate, and the stars spiral inward faster and faster, like skaters pulling in their arms and spinning into a blur. What's being stretched and squeezed is not the stars alone, but the very distances between things. Space-time elongates and contracts as the waves hurry past at the speed of light. Down here on Earth, exquisitely patient instruments stand ready to notice changes so slight they defy everyday sense. Shifts in length, smaller than 100,000th of a proton's width. Yet they do notice. When a neutron star pair reaches its last moments, the frequency climbs into a frantic chirp. Hundreds of orbits pass each second, the stars circling one another faster than a helicopter blade. In those final heartbeats, the radiated waves carry away a staggering bounty. Mass energy equivalent to a few suns, dumped into the fabric of space-time in mere seconds. The death spiral tightens, the signal rises, and then contact. The touch is not gentle. The moment the stellar crusts meet, a flash of gamma rays flares, a brief, hard blink, followed by a softer, longer-lived light show, a kilonova. It is an explosion in slow motion by cosmic standards, brightening and fading over days and weeks. The universe itself seems to shudder. Detectors billions of light years away can register the passing tremor, a signature scrawl across their data that says, 2 city-sized stars have become one. Inside that furnace, something precious and violent unfolds. Nature reaches for the heavy elements by means of a process called rapid neutron capture, the R process. Atomic nuclei are battered by such an overwhelming flood of neutrons that they can barely swallow them fast enough. Nuclei balloon with neutrons until they become unstable and decay into new, heavier elements. Gold, platinum, uranium. The list reads like the contents of a royal vault and a reactor's core, minted all at once in a frenzy of nuclear alchemy. A single merger can turn out several Earth masses of gold and comparable hordes of other rare metals, then fling that treasure into space at a third the speed of light. Over ages, that enriched ash cools, drifts and seeds star-forming clouds. In the far future, it hardens into worlds, alloys into rocks, and eventually finds its way into rings, circuits, and living blood. The glow we call a kilonova isn't one color, one shell, one speed. The collision ejects multiple components. Some material tears away quickly and lights the initial gamma ray burst. Slower ejecta churn outward in layers, thick with freshly forged nuclei. As those newborn isotopes shed their excess energy through radioactivity, the debris balloon shines, a bloom powered by the decay of billions upon billions of tiny clocks, each nucleus ticking towards stability. For a short while, the combined light can rival hundreds of millions of suns, a gentle ember compared to a gamma-ray flash, but intense enough to be seen across intergalactic distances. You can rest easy here for a beat. If you enjoy sleep-soft journeys through the deep story of the universe, and you want more told in this calm, mindful cadence, consider, quietly, without breaking the mood, subscribing to and liking Space Historian. It keeps this little lighthouse burning. Now let's pull back until all of this fits into a single thought. Wind time all the way to the beginning. 13.8 billion years ago, everything that will ever become galaxies and dust, oceans and eyes, was compressed into less than a point, a state smaller than a proton, without width, height or depth. This is the moment we call the Big Bang singularity, where our language fails and our equations, as we understand them, give way. Temperature and density surge to concepts like infinite. Space and time have not yet been written as we know them. The 4 fundamental interactions, gravity, electromagnetism, the strong nuclear force that glues nuclei, and the weak force that changes one kind of particle into another were not distinct. They were facets of a single, blisteringly powerful interaction, a unity we have not recreated since. In the first sliver of a second, shorter than the timelight would need to cross a proton, the universe underwent a sprint called cosmic inflation. Space didn't burst into an existing room, it created the room as it grew. In a breathless instant, distances ballooned by factors beyond human analogy. Tiny quantum jitters were dragged to astronomical scales, the wrinkles that would later become the scaffolding for galaxies. During this white-hot dawn, even the forces could not keep their separate identities. The superforce held sway. As the young cosmos expanded and cooled, symmetry shattered in stages. Gravity stepped apart first. Later, the strong force separated. Later still, the electroweak unified force split into electromagnetism and the weak interaction. Each break was a phase transition, like water crystallizing into ice, releasing energy and locking in the rules that would govern everything to come. In the first minute, conditions settled enough for the simplest nuclei to coalesce. Free protons and neutrons, themselves born when quarks found they could hold together, fused into light elements in a process we call Big Bang nucleosynthesis. The yield was simple and profound, mostly hydrogen, a good share of helium, traces of lithium, seeds for the chemistry of stars. Matter and antimatter, made in near equal measure, collided and annihilated, flashes of pure energy washing across the early cosmos. A slight excess of matter over antimatter survived. That tiny imbalance is why anything exists to notice any of this. For hundreds of thousands of years, the universe remained a fog. Hot, dense plasma, where free electrons scattered light at every step, making it impossible for photons to travel far without getting redirected. The cosmos was radiant but murky, bright and opaque, a glowing milk that concealed its own depths. Then came a clearing. As expansion continued, temperatures dropped enough for electrons to bind to nuclei and form neutral atoms. In that recombination, the fog thinned. Light could finally roam, unimpeded. We still see that afterglow today as the cosmic microwave background, a faint, uniform whisper of microwaves arriving from every direction, the cooled echo of first light crossing an ever-widening room. It's important to remember what the Big Bang was and wasn't. It wasn't a bomb in empty space, it was the flowering of space itself. It wrote the clock as well as the stage, set the constants, and delineated the possibilities, from the twitch of a quark to the weave of a galaxy. No later event has matched its authority to establish reality's ground rules. And yet even this genesis may not mark the end of nature's appetite for extremes. The universe has reserved other displays of power for later acts. When truly massive stars reach their end, 50 suns in one, and when they spin with ferocious speed, their deaths can transcend ordinary supernovae. The result is a hypernova, a blast so muscular that it dwarfs its more common cousins by factors of 10 to 100. It's not a single bomb, but a symphony of energies pouring out over time, the equivalent of billions of atomic bombs detonating every second, sustained across spans that, in cosmic terms, count as moments, but in human terms could encompass eras. The recipe is precise. The core collapses and becomes a black hole almost immediately. But rapid rotation frustrates a simple, symmetric implosion. Instead, the collapsing stellar interior spreads into a blazing accretion disk around the newborn hole. The disk's relentless spin winds magnetic fields into tightly coiled springs, storing stupendous energy in their twists. When those fields reconnect, snapping like cables under too much tension. They hurl matter and energy out along the poles at 99.9% of light speed. These jets drill through the dying star, emerge into space, and we detect their fury as gamma-ray bursts from billions of light-years away. Inside, the shock from those jets turns the star's layers into a brief layered furnace. Carbon flashes into neon, neon into silicon, silicon into iron. Fusion chains that would take ages in a normal core now happen in seconds. The extra energy from this runaway burning only deepens the violence, driving an explosion so bright that, for a while, it can be seen across cosmological distances. Hypernovae are rich smithies. They forge large amounts of heavy elements, including unstable isotopes that glow as they decay, powering afterglows for weeks and months. They can overrule the fate of their neighborhoods too. The strongest of them throw shockwaves that compress nearby gas clouds, triggering fresh rounds of starbirth while soaking the broader region with heat, delaying further star formation for millions of years. Their influence can span hundreds of thousands of light years, reaching far beyond the star that perished. Step back further to scales where galaxies are just sparks in a much larger blaze. Galaxy clusters are the universe's largest bound structures, cities of galaxies, thousands apiece, embedded in oceans of thin, superheated gas and tangled in invisible scaffolds of dark matter. Picture two of these leviathans on a collision course, drifting together over hundreds of millions of years at thousands of kilometers per second. The Coma cluster is one such giant. Its mass totals something like 100 trillion suns. When clusters like these meet, the energy involved eclipses the combined radiance of every star within them by factors of millions. It is one of the grandest kinds of event to occur after the beginning itself. Dark matter, indifferent to everything but gravity, glides through the encounter like phantoms passing in a crowd. But the hot gas, the plasma that pools between galaxies, cannot help but smash into itself. Bow shocks rise and roll through the cluster medium at thousands of kilometers per second. The gas is heated to over 100 million degrees, hot enough to strip every electron from every atom, and it shines in X-rays with fierce clarity. Magnetic fields stretched and amplified by the maelstrom accelerate electrons to near-light speeds. Those electrons spiral along field lines, emitting radio waves that bathe whole megaparsecs in a faint ghostly glow, a radio halo larger than entire galaxies. The shock fronts act like cosmic sonic booms, compressing and scalding everything they pass through. Their energy, if tallied, would outstrip the output of billions of supernovae. Meanwhile, inside the colliding clusters, individual galaxies tangle gravitationally. Tides peel stars from their outskirts, strewing long, delicate streams of starlight that trace the grand choreography of the cluster's merger. Some galaxies are shaken into bursts of frantic star formation as their gas is squeezed. Others are stripped of fuel and quieted, their future skies emptied of new suns. The transformation is both violent and, in the long sweep of time, oddly graceful. The slow knitting of a larger structure from many smaller ones. Yet for all that we can see, measure and model, there are musings at the foundation that carry an entirely different kind of unease. Hidden in the vacuum, in the field that lends mass to particles, the Higgs field, lurks a possibility that is both austere and unsettling. What if the vacuum we inhabit is not the true floor of energy, but a ledge? Physicists call such a state a false vacuum. It looks stable, behaves stable for eons, but it isn't the absolute minimum. Imagine a ball resting in a shallow dimple on a hillside. A bump could send it rolling into a deeper valley we cannot see from here. If the Higgs field were to decay from our ledge to the deeper valley, it would do so by nucleating a tiny bubble of true vacuum somewhere, anywhere. The bubble would not be a gentle sphere of new air in old air. It would be a region where the rules are different. As it expanded, at exactly the speed of light, no message could outrun it to warn what lay ahead. There would be no dawn of its arrival, no sky-brightening wave front, only a sudden everywhere change when the bubble reached a place. Inside, the fundamental constants, masses of particles, strengths of forces, could shift. Atoms, as we know them, might become impossible. If the strong force weakened, nuclei could come apart. Chemistry would dissolve into a silence of possibilities that cannot build complexity. Life would not die. It would be unmade. The energy bookkeeping is as stark as the scenario. The difference between the false vacuum's energy and the true vacuum's energy would be released as the bubble expands. That liberated energy could dwarf the rest mass energy of all familiar matter, a transformation more fierce than turning every proton, neutron, and electron in the universe into pure light. It would be a flood more powerful than all stars and galaxies together. We would not feel it coming. We would not witness it pass. Reality would simply become something else. For now, calculations, tinged with uncertainties, but sobered by what we know, suggest our vacuum might be metastable, not obviously doomed, not guaranteed safe, balanced precariously on the edge of stability. High-energy happenings, cosmic rays slamming into the vacuum, or the last sighs of evaporating black holes, could, at least in principle, flick the switch. Even without a spark, quantum chance alone might bud a bubble of truer vacuum out of what looks like empty space. That is the unnerving thing about vacuum decay. If our vacuum is only metastable, then its fall isn't a matter of asterisk if asterisk but asterisk when asterisk. Quantum mechanics promises that any perched on the ledge state, given enough time, will eventually tumble. And across the immensity of cosmic ages, events with vanishingly small odds rise to near certainty. Such a transition would be the universe's ultimate reset, merciless and absolute. Every star, every planet, every living story would be wiped clean, replaced instantly by a reality with different rules. No fossil of our world would remain, not even a memory, because memory itself would be remade. Some ideas go further. Perhaps this has already happened more than once in places beyond our horizon. Each decay could have blown a new balloon of space-time with its own constants and laws. We might be living in one bubble among many, neighbours to realms whose physics would feel as alien as dreams. Wind the film back to the first flickers after the Big Bang, when the cosmos was smaller than an atom, yet more crowded than a neutron star's heart. In that press of energy and pressure, tiny lumps in density could have collapsed into black holes, not the kind born from dying stars, but primordial black holes, massive as mountains, or as light as a paperclip, yet smaller than atoms. Their gravity would be wickedly compact, warping space and time on scales a human eye could never resolve. Unlike their stellar cousins, these firstborn holes could have formed with almost any mass. The most diminutive would be thoroughly quantum, where the crisp geometry of Einstein's relativity sparred with the probabilistic shimmer of the quantum world in ways we scarcely know how to model. Picture one with the heft of a mountain, crammed into a size below a proton's diameter. Its gravity millions of times more intense than anything we can summon on Earth. Around such an object, distance and duration would fray. Clocks would wander, rulers would lie. These microscopic monsters would also be among the universe's most dramatic pyres. According to Stephen Hawking's calculations, black holes glow faintly, leaking energy and slowly evaporating. The smaller the hole, The faster the leak, the faster the leak, the fiercer the end. A primordial black hole with the mass of a big asteroid would finish its life in a final incandescent detonation equivalent to millions of hydrogen bombs. In the last heartbeat of a truly tiny one, the rate of evaporation would shoot skyward. In a single second, it could disgorge more energy than our sun makes in a year, poured from a point smaller than an atomic nucleus. If such relics exist in abundance, they could answer a riddle that has haunted cosmology. Dark matter. Invisible to light yet heavy in the ledger of gravity, dark matter seems to sculpt galaxies and clusters without ever glowing. Primordial black holes would fit that bill perfectly. Pure gravitational fingerprints, no photons attached, and so the hunt ranges far and strange. Astronomers search in stellar flickers for the lensing wink of a compact mass drifting between us and a background star. They consider what would happen if one threaded a star's interior, how it might heat the plasma and change the star's shine. They ask whether collisions between primordial holes and neutron stars might leave gravitational waves we could catch. Over time, some of these small black holes could have fattened, swallowing gas, merging, growing into larger beasts that now lurk in the gulfs between stars, invisible except for the way their gravity bends passing light. The most massive seeds might even explain the otherwise puzzling speed with which supermassive black holes appeared in the young universe. Primordial kernels giving head starts to the giants at galactic hearts. Now, turn to the most furious expansion in history. Before the universe was even a second old, space itself lunged outward in a blink, an episode called cosmic inflation. In less time than it takes light to cross a single proton, the universe swelled from smaller than an atom to larger than a grapefruit, an analogy that still undersells it. In about 10 to 35 seconds, volumes increased by at least 10^26, as if an atom became vaster than the solar system in a flash. This was not movement through space. It was the creation of new space, everywhere, all at once. What drove that dizzying growth was a quantum field, the inflaton, filling the cosmos with an enormous energy density. Unlike normal matter, its energy didn't thin away in the usual way. As space grew, the field's peculiar equation of state kept the expansion fed, like a fire pulling fuel from the very air it heats. The larger space became, the more energy there was to drive growth, a feedback loop written into space-time itself. Inflation solved deep puzzles, exotic relics predicted by early high-energy physics, topological defects, odd particles, would have been stretched beyond our visible patch, which is why we don't see them. Regions that once touched were hauled beyond any possible contact, yet they still share nearly identical temperatures in the cosmic microwave background. Inflation explains that eerie uniformity. Quantum jitters in the inflaton field were amplified to cosmic sizes, becoming tiny over and under densities, the first seeds of everything from stars to superclusters. Those ripples are the blueprint etched on the sky. The energies involved beg a metaphor. In a slice of time too thin to picture, the inflaton dumped more usable energy into the universe than every star has radiated over 13.8 billion years. When inflation ended, its stored energy cascaded into a wildfire of particles and photons, reheating the cosmos to breathtaking temperatures, on the order of 1028 degrees. In that furnace, particles were made and unmade in torrents that make stellar cores seem cold, and perhaps it didn't happen only once. Some models sketch an eternal inflation, where bubbles of stop and start arise endlessly, each budding a new, causally isolated universe with its own settings. In that view, our cosmos is one room in an endless growing mansion. Meanwhile, other engines of extremity brew in the hearts of dying titans. Imagine a collapsing star spinning 1,000 times each second, its magnetic fields 1,000,000,000,000 times Earth's, an instrument tuned for cataclysm. This is a magneto-rotational supernova. Rotation and magnetism together, conjuring an explosion that can outmuscle even many gamma-ray bursts. As the core implodes, angular momentum is conserved. Like a skater tucking in during a pirouette, the spin skyrockets. What began with an Earth-sized core ends with something just about a dozen kilometers across, whirling millions of times faster than before. Magnetic field lines frozen into the infalling plasma are wound tighter and tighter, amplified toward the very limits of what physics permits. Fields this strong do not merely guide charged particles, they push back on space-time structure. Magnetic pressure rivals the pressure inside atomic nuclei. Stressed lines store titanic energy. When they snap and reconnect, they release it in detonations that make solar flares look like size. The result is a cosmic dynamo, an engine that accelerates particles to energies our laboratories cannot dream of. Protons are hurled so hard that their sheer motion can shatter nuclei on impact. Magnetic explosions punch out jets of plasma at velocities skimming the speed of light. Unlike many jets powered mainly by gravity, these magnetically driven beams can keep a ruler-straight focus for intergalactic distances, the kind of aim that could scour a biosphere from millions of light-years away if pointed carelessly across a living world. Fields climbing past 1015 Gauss twist the quantum vacuum into something birefringent. Space acts like a crystal, splitting light into polarized lanes. Chemistry itself deranges under such fields. Atoms elongate into needles aligned with the field. Molecular bonds torque into unfamiliar shapes, and even the behavior of fundamental particles starts to stray from our everyday instincts. A magneto-rotational blast can outshine a typical supernova by hundreds of times, forging exotic, neutron-rich isotopes in brief, violent foundries. Many of these nuclides exist for instants, then decay towards stability, painting the afterglow with their changing light. It is alchemy written at terrible scale, pushing nuclear physics to its edges. And through all of this, the fireworks we see and the tremors we infer, there is a heavier, quieter presence shaping the stage. In the wide halos around galaxies, an unseen substance outmasses the stars by roughly 5-1. This dark matter heeds gravity while ignoring almost everything else we understand, a shadow architecture that sculpts cosmic structure while staying dark to our eyes. If its particles are their own antiparticles, then when two meet, they should vanish into pure energy. Einstein's ledger tells us what that means. A single kilogram annihilated would release the energy of about 21 million tons of explosives, the most efficient conversion nature allows in our current playbook. In the dense hearts of galaxy clusters, where dark matter piles highest, such annihilations could set off cascades of high-energy particles and gamma rays, brief storms that might outshine the combined starlight of the cluster. Some theories push their masses sky-high, far heavier than protons, so that each annihilation would be a spectacular shower, birthing exotic particles unseen in ordinary nature. The telltale could be pairs of gamma-ray photons at specific energies, a spectral signature of dark matter's disappearance. In the most extreme imaginings, those photons could reach towards scales where quantum gravity begins to matter. The ragged edge we call the Planck regime. If annihilation prefers the densest pockets, it might not be just pyrotechnics. The energy could heat surrounding gas and keep it puffed up, delaying or preventing it from collapsing into stars. Feedback written not by supernovae or black hole jets, but by the quiet violence of the dark sector itself. And near black holes, where gravity funnels everything, dark matter included, into tight concentrations, annihilation might roar. Densities could climb high enough that the rate of destruction contributes not just a whisper, but a notable fraction of the local power budget, adding its invisible hand to the visible violence until it could contribute significantly to the total energy output. High-energy outbursts, brief flares of gamma rays, or ghostly showers of neutrinos might be the fingerprints of something darker at work, pockets where dark matter piles up and then quietly destroys itself in pairs. In some speculative pictures, each annihilation is more than a single spark. The released energy reshapes the local environment, briefly making it even more likely that nearby dark matter will meet and vanish. In that scenario, a cascade could follow, a chain reaction that sweeps a region clean, leaving behind a haunted void brimming with hard radiation and very little else. To look for such whispers, astronomers aim their most sensitive instruments at the universe's harshest addresses. The crowded hearts of galaxies, where gravity gathers dark matter most tightly, are prime suspects. If annihilation leaves a spectral calling card, sharp gamma-ray lines, specific blends of high-energy photons, then a galactic center should be where the signal peaks above the noise. So far, though, the sky has stayed demure. The absence of a clear, consistent signature hints that dark matter may not self-annihilate, or does so far more rarely and reluctantly than early models imagined. Meanwhile, across interstellar space, nature runs accelerators that make our greatest machines look quaint. Somewhere, protons are being whipped up to speeds so extreme they move at 99.9999% of light's pace, each one carrying the punch of a 60-mile-per-hour baseball packed into a single atomic nucleus. The most energetic of these cosmic rays that ever reach Earth carry more than 1,020 electron volts, over 10 million times what the Large Hadron Collider can impart. One such particle could, all by itself, flicker a small bulb if its energy were surrendered at once, and yet it's smaller than a proton. When a cosmic ray slams into the upper atmosphere, it blossoms into a shower, cascades of secondaries that fan out across the sky, triggering detectors strewn over thousands of square miles. Where do these bullets come from? For middling energies, supernova shockwaves, vast rolling fronts of compressed plasma, can do the job, boosting particles little by little each time they cross the shock. But beyond a point, supernovae run out of steam. To reach the truly absurd energies, the universe needs mile-deep wells of voltage drawn across distances measured in millions of light-years, a feat no star's death throes can sustain. Active galactic nuclei, black hole engines at the cores of galaxies, look like the best culprits. Their magnetic fields can hoard phenomenal energy and release it in spurts, lashing charged particles forward to near-light speeds. Their jets are natural synchrotrons carved in space, accelerating particles along field lines for distances no human-built experiment can approach. But there's a catch. Magnetic fields don't just accelerate, they also deflect. For most cosmic rays, the journey through tangled galactic magnetism sends them pinballing so thoroughly that their paths forget where they began. Only the highest energy particles, above about 1019 electron volts, can fly nearly straight through the Milky Way's magnetic fog, offering the slimmest chance to point back to a source and say, "There." As these charged voyagers corkscrew around field lines, they shed light, synchrotron radiation that paints the sky in radio, X-rays and beyond. Much of the Milky Way's radio glow is this very hum, electrons spiraling along the galaxy's magnetic threads. But shocks aren't the only route to extreme energies. Magnetic reconnection, when braided field lines snap and rejoin, can fling particles outward in sudden explosive bursts. And perhaps there are stranger engines still. The slow decay of heavy relics left from the universe's first moments, particles from realms beyond our standard model, quietly disintegrating into torrents of ultra-energetic secondaries. However they are born, cosmic rays don't travel alone. Their collisions with gas and dust create telltale messengers: gamma rays, neutrinos, positrons, that carry clues about both the rays and the environments they traverse. By reading those secondaries, we map the invisible scaffolding of our galaxy in ways our eyes never could. Now, let your thoughts float into the hush between things, between atoms, between worlds. The vacuum is not an empty, silent room. It seethes. Virtual particles wink into being and vanish again in instants so brief they're beneath the threshold of direct observation. This is the zero-point energy of the quantum vacuum, a low murmur that persists even at absolute zero. Every tiny parcel of space is thick with evanescent pairs, photons, electron-positron twins, and countless other brief alliances, borrowing energy against a ledger that must be balanced in a time short enough that quantum mechanics permits the loan. On paper, the energy density of these fluctuations looks ludicrous. Simple calculations suggest a value about 120 times larger than what the universe calmly displays. An absurd mismatch called the cosmological constant problem. If the naive number were right, space would be so overcaffeinated that atoms couldn't cohere, stars couldn't form. And yet, though the vacuum's roar is somehow muted to a whisper on cosmic scales, its presence is measurable in delicate ways. Bring two uncharged metal plates almost impossibly close, and a pressure appears, pushing them together. The Casimir effect, a tiny force born from the vacuum itself. Near a black hole's edge, virtual pairs can be split, one falling in, one escaping, turning the vacuum's bookkeeping into real outgoing particles. That trickle of Hawking radiation slowly drains the whole of mass, a conversion of vacuum jitters into tangible light. In the infant universe, inflation stretched those quantum ripples in energy to cosmic size. Microscopic fuzz became macroscopic patterns, minuscule overdensities that gravity later amplified into stars, galaxies, and clusters. Every leaf of every tree, every circuit and cell traces its ancestry to a quantum quiver when the universe was smaller than an atom. Some daring ideas go further and suggest that even our entire universe could have been a vacuum fluctuation, not from nothing precisely, but from a quantum nothingness that flipped into being and couldn't flip back, its tab repaid by the slow arithmetic of cosmic expansion. If we could learn to persuade the vacuum, to adjust its boundaries, to summon negative energy densities, to choreograph which modes of fluctuation are allowed, then in theory, we might tap an energy source that is everywhere. A cup-sized device feeding all of civilization for eons is the kind of image that floats into such discussions. For now, it's a dream with thorny physics, but dreams have been blueprints before. Beyond our farthest light, beyond the longest ladder of galaxies we will ever see, lies a possibility so expansive it reframes everything: the multiverse. If eternal inflation is the rule rather than the exception, then our Big Bang wasn't a solitary spark, but one ember among countless fires, each a separate universe budding off within an inflating false vacuum. New regions, each with their own dial settings, the strengths of forces, the masses of particles, the very grammar of physics, would be born ceaselessly, a branching grove of realities growing without end. In some, gravity might be stronger, crushing stars into brevity. In others, electromagnetism might drift out of tune, making atoms brittle or impossible. The strong force could soften or stiffen, shutting down fusion or permitting exotic elements we cannot even name. In an infinite ensemble, total energy is unbounded, and every allowed history happens somewhere. Some regions would expand forever, others would recollapse in their own quiet big crunches. Still others might pulse in cycles like cosmic lungs. In certain interpretations of quantum mechanics, the multiverse is closer than far away. It's every possible outcome of every quantum measurement, unfolding in parallel branches that quilt reality with alternatives. Against this immensity, the anthropic principle offers a simple compass. We observe a universe whose numbers let observers exist. In a sea of options, we are necessarily in one of the rare bays where chemistry blooms into consciousness. If, in the far future, communication between universes were more than fantasy, the exchange of knowledge would explode our conception of science, ideas from other physics flowing into ours like new elements added to a periodic table. Some imagine an ultimate settling too. False vacuum regions consumed over eons by expanding bubbles of the true vacuum. A slow selection that leaves only the most stable rules standing across all that is. We have drifted from the quiver of quantum foam to the breadth of a possible infinity, visiting powers that press against the edges of comprehension. In your body, the strong force stitches nuclei together. In stars, fusion writes light on the dark. Across space, gravity and dark energy argue over the shape of the future. And you, aware, reflecting, are one of their outcomes. The calcium in your bones was minted in stellar detonations. The iron in your blood was lifted from a dying star's heart. The gold that gleams in a ring was brewed in the furious embrace of colliding neutron stars, in a spray that rattled space-time itself. We are not visitors to the universe's engines. We are the ash and light they left arranged into thought. If you'd like more of these sleep-soft journeys, slow stories about deep time and deeper forces, please gently subscribe to and like Space Historian. It keeps this quiet lighthouse lit for your next night under the stars. 13.8 billion years of unfolding have carried you to this moment, with a mind capable of tracing the thread back through forces and fire to the first hour. So what is the greatest power in existence? Perhaps not a single force, but the universe's unsated creativity, its gift for turning hydrogen into stars, stars into heavy elements, elements into worlds, and worlds into places where awareness wakes and asks how it came to be. The next time you look up, remember you are seeing the ongoing dialogue between powers vast and subtle, and that your own attention is one of their finest achievements. Through you, the universe studies itself, brighter than the full moon, even from galaxies billions of light years away. In a handful of seconds, the energy released exceeds what 10 trillion hydrogen bombs could yield if they detonated every second for the age of the universe. The most powerful gamma ray burst yet found, the boat, the brightest of all time, flashed in October 2022, overwhelming detectors around the solar system and nudging Earth's upper atmosphere from some 2 billion light-years distant. Imagine standing here and seeing a torch at Alpha Centauri flare like a car's headlamp. That's the scale of it. These signals arrive after journeys spanning eons, messages from deaths long before our sun was born, from epochs when stars ran hotter and wilder than those of today. Some bursts set out less than 1 billion years after the Big Bang, lanterns from the universe's youth, when massive stars lived fast and died hard, sowing the seeds for the elements that later built planets and people. But compared to what lurks in the darkness between galaxies, even these titans pale in comparison.